Hey guys, today's short video is part of our introduction to positivism and statistics. Today we're going to discuss the structure of statistics and statistical significance and modeling. Just a brief introduction to kind of get us going on our topic, and obviously we'll fill in more as the course goes on. Generally, we divide statistics into two different groups, two different topic areas: descriptive versus inferential statistics. Most of you are very familiar and probably comfortable with descriptive statistics. Admittedly, they can be complicated, but at heart, they're actually pretty simple. For example, if we draw a sample of individuals, as the Pew Internet people did in 2007, they drew a sample of 935 teenagers, and they found out that they were trying to look at who's creating content among teenagers, online content. They found a couple of different things. They found out that 64% of teenagers were creating at least one type of content, and that had increased since 2004. Girls tended to dominate in this area. That is, they created more content than the boys. When we do descriptive statistics, we're really talking about two large categories of statistics: central tendency and measures of dispersion. Central tendency are things like averages, different kinds of means. Measures of dispersion are different kinds of measures of variability of the data. Are the responses homogeneous or heterogeneous? What's interesting to us, or what the next question may be, is why should we care about the opinions of 935 people that we don't know when we have a nation that has over 20 million teenagers in it? And that's the topic of inferential statistics. In inferential statistics, we apply probability theory to help us make decisions about populations. That is to say, we tend not to know much about populations. We don't have data on the populations. We take a sample instead. Think of a population as being the ocean, and think of a sample as being a bucket of water drawn from the ocean. What can we learn from that bucket of water that allows us to understand the larger ocean? The kinds of statistics here are things, and the things we'll cover in this class are the t-statistic, the f-statistic, and chi-square. These particular statistics allow us to, based on our sample, our bucket of water, to generalize about the larger population, about the entire ocean. So, for example, while we know that from that survey, the descriptive statistic was that 64% of teenagers were creating online content, we actually have an estimate that is 64% plus or minus 3.1%, and that's the 95% confidence interval. Many of you have already encountered confidence intervals, but if not, don't worry. This is definitely something we will cover and make understandable to you in this course. Let's talk a little bit about descriptive statistics and where we go with this. The heart of this is of taking samples. And in an ideal world, we'd like to have a random sample of individuals. Truthfully, we don't often have true random samples, but we take samples that actually are very similar to random samples, and similar enough that we can apply different statistical techniques as if they were random. What a random sample allows us to do is to make an inference about the population parameters and give us a certain level of confidence in the kinds of estimates we're creating. Now, let's parse this out a little bit. What is a population parameter? What is a statistic? A parameter is a statistic based on a population. So if we could have access to all of the teenagers in the United States, all 20 million teenagers, we could calculate the percentage of them who create online content. We wouldn't need any inferential statistics. The trouble with this is that it's very expensive and complicated to get to those 20 million people. So instead, we take a sample. The sample doesn't provide a parameter, like a mean. It provides a parameter estimate, which is also a mean. So what happens is we take a sample to produce a parameter estimate, which estimates the parameter of the population. Then we use statistical significance testing to help us, make a statement about how likely the statistic we observe from our sample could be produced by a population. And during this course, we're going to put together these two branches of statistics, both the descriptive and the inferential, to allow us to make decisions about data and about our hypotheses. And we'll learn why small samples, what appear to be small samples, 935 teenagers out of 20 million, can produce surprisingly accurate estimates of what's going on in the general population. You really can't talk too much about hypothesis testing and tests of significance until we understand something about making propositions or declarative statements about our variables. So we can talk about three different kinds of propositions. The first one is a univariate proposition. In this case, univariate means a single variable. For example, I could make the declarative statement, or my proposition is that most college students drink alcohol at least once a week. I don't know if that particular statement is true or not, but it lends itself to being empirically verified. The variable that I'm looking at is the frequency of drinking. So this is something that a priori, I don't know whether there's a lot of drinking or a little drinking among college students, but I develop a hypothesis or a proposition which captures my hypothesis. We should also understand the unit of analysis. It's a good idea anytime you're looking at data to understand exactly what it is you're measuring. In this case, my unit of analysis is individual college students. Maybe I have the ability to go out and do a survey and ask college students about their drinking habits. And then finally, there's the statement itself, and the critical word in this particular statement is the word most. That is, most college students drink once a week or more. Moving on, we have a second kind of proposition that we can make, which is a bivariate proposition. Here we have two variables. Bivariate in this case implies two different variables. And I'm going to distinguish those variables with the notation dv and iv, where dv stands for dependent variable and iv stands for independent variable. In general, the thing that we're interested in is the dependent variable, and it's not something I control for. The independent variable on the other side is the thing I always want to compare across. I think there might be a difference between men and women with regard to the frequency of drinking. So here's my statement. Men drink alcohol more often than women. My variables, I have two of them. My dependent variable is frequency of drinking. My independent variable is gender. Then I give a statement which shows the relationship, the hypothesized or believed relationship existing between those variables. Men drink more frequently than women. And so here we see that there's two important parts to that statement. First, the more, and the second, men compared to women. Men drink more frequently than women. If the world was simply a bivariate place, then we'd be in very good shape developing univariate and bivariate propositions, and our statistical analyses would be quite simple. But it turns out that we live in a multivariable world, particularly when we look at social behavior and in sociology in particular. So let's look at a more complicated multivariate proposition, where here I'm going to put in three variables. Notice that my three variables are in two different categories. The first is dv, dependent variable, and the second is iv, independent variable. But I have two independent variables, and I'm going to get to those in just a minute. Here's my statement. Among non-depressed students, men drink alcohol more often than women. But among clinically depressed students, men and women drink alcohol equally often. Again, I don't know if those two statements are true or not, but they can be empirically tested. So let's walk through the variables. My dependent variable is the same, frequency of drinking. My major independent variable is gender. Again, I'd like to compare men and women. But now I've added a third variable as a control variable, because it seems to me that if we can assess whether somebody is depressed or not, that their drinking habits may vary, and they may vary by gender. So to take that big proposition at the top and break it down into two separate statements, statement number one is, if I have non-depressed students, if I have a sample of non-depressed students, I think male students drink more than female students. If I have a sample of students who are depressed, I believe that male students will drink the same amount as female students. We can add in more control variables and more explanatory variables. In this case, gender is an explanatory variable, and we can develop very complicated models, most of which are beyond the scope of this course, but would be well within your understanding and ability to calculate and interpret in your next statistics course. Now, it turns out that there are different kinds of statistics that we can calculate for linear models versus nonlinear models. Nonlinear models are more complicated and are beyond what we'll cover in this course. We're going to stick to linear models. So let's take a look at this example down here on the lower left. There's a variable in the General Social Survey called EDUC, which is the number of years of education of the people taking the survey. And there's another variable called PRESTG80, Prestige 80, which stands for occupational prestige. When I produce a scatter plot, it allows me to look at the relationship between these two measures. I've drawn a line through the scatter plot to show the general direction. And what this is showing us is that, on average, as the number of years of education increase, on average we see an increase in occupational prestige. For people like yourselves in college, this is hopefully good news. That is, more education tends to be associated with additional occupational prestige or higher occupational prestige. The line drawn through there is meant to show the general nature of the relationship between these two measures. And you'll notice in the upper right-hand corner of that graphic, there is a formula and something called R squared. The formula, y hat equals 14.6 plus 2.2x, describes the relationship between education and prestige. It's something we'll discuss by the end of the course and something you'll be able to understand and interpret. And right now it's probably just a little bit of a mystery. Let's take a look at another example. This scatter plot on the right-hand side shows the relationship between people's age and between their sexual frequency. You'll notice that there's banding in this chart, in this graphic. And the banding is due to the sexual frequency variable, which is measured and has 7 categories. So it's not really a number the way you think of it. It's not 20 times per year or 30 times per year, although I've made an estimate of that. But people pick categories that they fall in, and then I've interpreted those categories to be number of times per year. Notice here that the line drawn through the graph is now declining as we go from left to right. The implication here is that the relationship between these two variables is that as people get older, on average they report lower sexual frequency per year. And again, in the upper right-hand corner of the graphic, I show you a formula that describes the relationship and a descriptive statistic called R squared, which gives us an idea of the strength of the relationship. Again, I'm leaving those unexplained for now, but we will definitely get to them by the end of the class. These two relationships appear to be linear. And by linear, we mean they are either monotonically increasing, like the relationship on the left, or monotonically decreasing, like the one on the right. And that simply means that as we increase on one variable, on average, the other variable goes up as well as we go from left to right, or that as we move from left to right on the age variable, for example, the sexual frequency variable declines. That would be a monotonically decreasing relationship. What we're not seeing here are any changes in direction of the relationship. If we saw a change in direction of the relationship, we would have evidence of a nonlinear relationship. And most of the nonlinear estimation routines that we would teach in a statistics class are beyond what we would teach in an introductory class. Here's an example of a nonlinear relationship. Here we have on our x-axis gross domestic product per capita measured in thousands of dollars of U.S. currency. You can see that from left to right, we start with very low gross domestic product per capita, and we go up to very high gross domestic product per capita. On the other axis, we have a life expectancy variable. This is the average age that you expect a person to live in each particular country. Now, notice that the points plotted here are all different sizes, and what I've done is I've weighted or made the size proportional to the number of people living in a country, so that it gives us a sense of whether the better performing countries economically and in terms of life expectancy are the bigger countries or the smaller countries or the medium-sized countries. I've also drawn a line through this graph, this visualization, and notice that it's not a straight line. That as we go from left to right, as gross domestic product increases, indeed it appears that life expectancy increases. But it increases up to a point and then begins to level off, and in some cases maybe even decrease a bit, so that gross domestic product has a positive effect within one range of data and has a negative effect within another range of data. These kinds of nonlinear models are very interesting and fairly common, but again, beyond the scope of this class. We're going to stick with linear models.